Okay, so I'm not going to wait. I have to start now. Today we have a very tight schedule. We got a very complicated algorithm to discuss. So last lecture we have we only had a very lightweight discussion for two algorithms that are based on depth first search, which are the DFS algorithm and also the but that are based on DFS, which are topological sort and strongly connected component. So today we're going to learn something that is very different. That is very different from that. So let me see, how could I open up my this one? So okay, so so today we're going to learn a totally new algorithm named minimum spanning tree. And so in minimum spanning tree, the problem definition is that we're giving an undirected graph G, and also we associate each a weight for each edge in the graph. We associated with a weight. So this may seem kind of like new to you, but so here I'm just going to use an example to explain. So so here, let's say when we're talking about the Biden plan. So probably you know that the new president wants to rebuild the infrastructure for the America. So let's just talk about the road. So for example, if we have here the Boston and here the New York, here is say DC, and then this is, for example, Miami, and then we have Philly.
Hey, Professor, you sharing your screen?
Oh, I didn't share my screen. I'm sorry. I'm totally sorry about that. I forgot that. Okay, I'm sorry. Okay, so okay, can you say it?
Yeah, now.
Okay, sure. You don't miss anything, because previously I was just talking about the depth first search and topological sort and strongly connected components. So today we're going to learn a new algorithm named minimum spanning tree. But so first I need to explain what is minimum spanning tree. So here, let's say in the definition of the minimum spanning tree problem, the input is a undirected graph and a weight associated with each edge. So for now, I'm just going to spend maybe 5 minutes to explain why do we need to associate a weight with each edge in the graph. So here, let's say we talk about the road network, and say, for example, we got a couple of several major cities in the metropolitans in America. So like Boston, New York, DC, Miami, Philadelphia, and Seattle, and also LA. So suppose our aim is to say build a road to get all these cities connected, So if previously when we learned the BFS algorithm, so here let me show you the BFS one. When we learned the BFS algorithm, so here we, as you can see in the example, we take so this is the output, and in this problem we say our source is this node S, and then in BFS the output is the minimum distance from the source node to every other node in the graph. So what it says is that from source node to the node Y, the minimum distance is 3, correct?
Yep. Yeah.
Okay, and this is the route that gives us the distance 3. So here we got distance 3 because we need to go 3 rows or follow 3 edges or 3 hops to go from the source to Y, correct?
Yep.
Okay, basically in DFS, we don't we don't have a weight for any edge, and basically we take each edge the same. We say, okay, this edge has a distance 1, this edge has a distance 1, this edge has a distance 1, correct?
Yes.
Yes.
Yes, so that's why we finally get the total distance of 3. So 3 basically means 3 edges or 3 hops. But in practice, so in a lot of situations, let's say if I tell you, okay, from Los Angeles to Boston, you need to go, let's say 4. The distance is 4. If we use the Bfs algorithm, it will tell you, okay, the minimum distance is 4. And also it will also tell you, let's say from Boston to, if you want to go to Miami, the minimum distance is also 4. So this is the, so here, this is the road to go from, sorry, this is the road to go from, let's say, let's say here, this is the road, the route that we need to follow to go from Los Angeles to Boston, and this, sorry, to Miami, and this is the road that we need to follow to go from Boston to Miami. So if we use Bfs algorithm, the algorithm is going to tell you, okay, so if this is our source node, if Miami is our source node, then to reach LA and also to reach Boston, the minimum distance is both 4, correct?
Yeah, correct.
Yes, so because to go from Miami to Boston, we need to go across 4 edges. To go from Miami to LA, we also need to use 4 rows or 4 edges. But I mean, is the distance or the total travel distance the same? So basically, if you go from Boston, if you go from Miami to Boston, it will probably be the total travel distance is going to be around 1,000 miles. Whereas if you want to travel from Miami to Philadelphia, sorry, Miami to LA, the total distance may be 3,000 miles. Correct?
Yeah.
So
Yes.
even though they use the same amount of edges, but the total distance should be dramatically different, correct?
Yep.
Yeah, so the main reason is that here, if we consider the length of each road, say for example, if you want to drive from LA to Seattle, this road may be, even though it's just 1 road, but this road itself may be 1,000 miles. And from Seattle to Philadelphia, it may be 1,500 miles. And from Philadelphia to DC, this is relatively close, let's say 100 miles. And from DC to Miami, let's say it's 700 miles, okay? So here you can see that each edge, basically, each edge, if we use each edge to represent a road, and then probably we should associate each edge with the distance of the road, how long is the road, because we need to differentiate them, correct?
Yes.
Okay, so yes, so that's the main reason why we want to associate a weight with each edge in the graph, because so it's, yes, every edge is an edge, but they may convey different meaning, or they may convey different distance or different cost. So that's why our input is this, and then so this is the input, basically is an undirected graph and a weight for each edge. And also here, this is the input and our output. So we want to output a subset of the edges in the graph that can help us to connect all the nodes in the graph, and also whose total weight is minimized. So let's say, what does that mean? Okay, so here I'm just going to remove these colors. Okay, so again, let's use these cities as an example, and I'm just going to associate each edge with a weight, which represents the how long is the road. So this road is 1,500 miles, 100 miles, and then let's say this is 200 miles from New York to Philadelphia. It's another. Oh, it's also, so this is 150. 150. From New York to DC is 200 miles, and from New York to Boston is 200 miles, and from DC to Miami, let's say it is 700 miles. Okay, so suppose that, and here is this. Okay, let's see, this road itself is 2,000 miles. Okay, so suppose here we let's consider maybe 200 years ago and 300 years ago, when at that time there was no road. But the federal government is looking to build some road to connect all the cities in our country. And here, if there is an edge between two cities, it means that it doesn't mean there already exists a road, but it means that if we want to construct a road that connects these two cities, how long should the road be? So because the government has a limited fund, so what they want to do is that they want to build the road, build some roads to get all the cities in our country connected. But at the same time, they want to minimize their cost, meaning that they want to build the least amount of road to get least the miles of road to get all the cities connected. Make sense?
Yeah.
Okay. So here, let's say, can someone give me your idea on how to build the road? Which road are you going to build to get the cities connected, all the cities connected? Okay, I'm just going to go for one example. Suppose that we're going to build this way, build the road in this way. I use the blue color to denote the roads that we actually construct. So suppose that we decide to build a road like this. Okay, so if we build the road in the blue colors, can we get all the cities in the country connected?
Yeah, right.
Yeah, because by saying that we get all the cities connected, what I actually mean is that from any city A, you can find a route to go to city B. Let's say from LA, can you go to Seattle? Yes. Can you go to Philadelphia? Yes. You can go to New York. You can go to Boston. You can also go to DC and Miami. So kind of like that. Yes, we get all the roads. We got all the cities connected, correct? With the blue roads.
Yep.
Okay, but say, how many miles in total do we need to build? How many miles of road do we need to build? Let's say we need to build, this is 1,000 plus 15, 1,000 plus 1,500 plus this 100 miles plus 200, 200 and 700. 200 plus 200 plus 700. Let's say how many, what is the total amount of miles? This is 1,200. So 37, right? Correct?
Yes.
Yes. Yeah. So if we build a road, if we want to build the road in this way, then we need to build 37,000 miles of road to get all the cities connected. And let's say maybe you have a better plan that can save us money. Can anyone propose a different plan? Do you have a different idea? Okay, I'm just going to name a random thing. Okay, so for example, we built the roads in purple color. So okay, suppose we build the road in purple colors. So with the road in purple colors, can we get all the cities connected? We're going to use LA as an example. From LA, can go to Seattle? Yes. You can go to Philadelphia. You can go to DC, New York, Boston, and Miami. Yes. So let's say how many miles of road we need to construct in total. 2,000 plus 1,500 plus this 150 plus 200 plus 200 plus 700. So in total, 30, 35, 36. It's going to be 48, 50 miles in total, correct?
Yeah.
Yeah. So here, what we say is that yes, with the same aim to get all the cities connected, if we come up with different plan, the total amount of efforts that we need to pay can be very different. So and here we definitely want to go with the plan in blue colors because it saves us money, correct?
Yes.
Okay, cool. So then the objective of the minimum spanning tree problem is basically to find a subset of the edges that can help us to connect all the nodes while the total weight of the picked edges is minimized, the same as what we discussed over here. So the most famous application of the minimum spanning tree problem is to do the infrastructure design. It can help us to find which roads should we build and to save money. Make sense?
Yep.
Yeah, it does.
Okay. So any question with the definition of the problem? Okay. If no problem, then I'm going to proceed. So here, let's say, so we got the minimum spanning tree problem, and to solve this problem, there are two algorithms. The first one is called Kruska. And this one we're going to ignore it because it's not that efficient and it's not so practical at all. So instead, we're going to learn an algorithm named Primal. So this is our focus today, and let me jump to that. Okay, so before jumping to the Primal algorithm, I'm here. I just want to show you another example of the minimum spanning tree problem. So here, say we get an undirected graph with the weights associated with the edges. So again, we want to pick a set. Basically, we want to pick up a subset of edges to get all the nodes connected and whose total weight is minimized. So here is the solution to this problem, to this input. Okay, so okay, and now we're going to discuss the Primal algorithm. So this is the pseudocode of the Primal algorithm. It takes three inputs. Our input arguments. G is the graph, W is the weight associated with all the edges, and then R. Do you know what does R mean? Guess what does R mean?
Range?
No, R is this. You can take R as this. Here is our example. Say R means that from which node do you consider to start building the roads? Okay, so this is, you can take it as, okay, we're going to start building the roads from LA. Okay, so basically we cut the route. So this is the first node that you are considering to build a road for. Okay, so it can be any node in the graph and it does not impact the final result. So no matter what kind of root node you use, the final output is going to be the same. Okay, and then let's look at the pseudocode. So for each node U that is inside the graph, that is a part of the graph. So we associated with a key that is infinity, and we associated with a pi that is nil. So have you seen similar kind of code before?
Kind of looks like BFS.
Yes, kind of like BFS. Let's check what we have in BFS. In BFS, what we do is that for each vertex, we associate it with the color. So so for now, we don't look at the color. We just look at here. we associate with the distance that is infinity, and we associate with the pi that is nil. So here so the only change is that we change the distance. We change it from distance to key, and also the initial value is infinity, and we also associate with the pi that is nil. Cool. So it's very similar to the BFS one. Okay. So what does pi denote?
That was the parent.
Yes.
node? Yeah.
Yes. We in BFS we basically use pi or the parent to find the shortest route from the source to any other node. Correct?
Yeah.
So here we're going to say think about a different way. So we are also going to use pi to do something. I'm going to explain it later. So first we associate the root node with a key that is 0, and then we create a queue that includes all the nodes in a graph. And while queue is not empty, so we have this U equal to extract min Q. Have you seen this function before, extract min before?
Was that in DFS?
No,
The implement? No.
no. So here, let's say, if we talk about the general queue, the queue that we have learned, so what is the remove function? How do we remove an element from a general queue? So sorry. What about, let's say, what kind of policy? So if we talk about a general queue, what kind of policy does it implement? First in.
First in, first out.
Yes, first in, first out. So if we call the remove function, what is the remove? Which function help us to remove an element from a queue? What is the remove function in queue? It is DQ, right? Correct?
Oh, yeah.
Yeah. So in DQ, if we're giving a regular queue, then if we want to remove some element, we need to call the DQ function, and it always removes the element that enters the queue the first. Correct?
Mm-hmm.
Okay. But here, so you can take Q as something as the doctor's waiting room. Okay, doctor's waiting room. So meaning that so whoever has whoever comes to wait for the doctor first is able to see the doctor first. But today we're going. So this queue is not going to be a regular queue. It is called a priority queue. Priority queue. Okay, so priority queue implements a policy that we always remove the element with the highest priority first. So and then the remove function of priority queue is called extract min. So you can take it as the doctor's the emergency room. So when we talk about emergency room, let's say there are 10 people waiting in the emergency room. Who is going to see the doctor first?
First
To
person.
queue the first person to enter.
No, it cannot be the person who. So I'm talking about in real life. Who gets to see the doctor first in the emergency room?
With the most urgent.
Yes, with
case.
the most urgent case. Yes. So basically, when we enter the emergency room, the doctor is going to, or the nurse is going to associate us with a priority or urgency. Okay. So whoever has the highest urgency can go to should be able to see the doctor first. Correct?
Yep.
Okay. So similarly here, for priority queue, we associate each element a key. So the lower the key is, it means that the more important is this node, the more urgent is this node. So each time when we want to remove an element, we basically call the extract min function to remove the element with the minimum key, or in other words, with the highest priority or with the most urgency. Okay, make sense?
Yeah, makes sense.
Okay, so the extract min function basically removes the element with the smallest key or smallest key means highest urgency. Okay, who has the largest so who needs to so that person really needs to see the doctor first. Okay, so every time we just remove the element with the minimum key, and then for each v that is adjacent to u, if v is inside the queue and wv meaning the edge, the weight of the edge between u and v is less than v dot key, we do some update. Okay, so let's use an example to go through the pseudocode. Okay, so this is the pseudocode. I'm going to get the example. So previously I take a picture of the example from my phone, so I'm going to pull it up. Okay, it's over here. Four, 8, 7, 9, 14, and 10, 2, 4, 2, 6, 2. This is 1. 7, 8. Okay. Okay, so this is an input graph, and suppose here we say that A is our starting node. So this is our starting node. So we take it as the root R. So this is our root. So we want to start building the rows or picking the edges from this node. Okay. So then let's go through the example together. So first, let's say for each U that is a part of the graph, for each node that is part of graph, we associate it with an infinity key and a neo parent. So what we do is this: we associate each node with an infinity key and neo parent. So we do this for all the nodes in the graph. And then, so we associate a 0 key with the root node. So here is our root node. So we change its key from infinity to 0. Okay, and next we're going to create a queue, that priority queue that includes all the nodes in the graph. So let's say we have this queue which includes all the nodes in the graph: A, B, C, D, E, F, G, H, I. And to make it clear, I'm going to write down their keys, the keys associated with them just below the nodes. So we have a 0 key for A, but for all the other nodes, their keys are just infinity. So we got 0, infinity, infinity, infinity. Okay, so, and this is what we have after this line, and before we enter the while loop. So while the queue is not empty, so is this true or false? Is the queue empty?
No, it's full.
No, so this is true, right? It's not empty, so it's true. And we call the extract mean function over the queue. Recall it. So remind me. So what does the extract mean function of the priority queue return? What does this function do? Here, it removes the element with the smallest key, correct? So over here, which element should we remove?
B.
No, it should be A, because A has a key 0. B has a key infinity. Yes. So here, what we do is that we remove this node A. We remove it from the priority queue, and then so we have U as A. So I'm putting U over here because U is the node A. So U is the node A. For each V that is adjacent to U, what are the neighbors of U or A?
B and H.
B and H. So it's B and H. So we first start V from B. So we put V over here. So this is the node V. And then let's say, is V inside the queue? Or is B a part of the queue?
Yeah.
Yes, it's over here. So this is true. And W, so next we're going to check WV. What is WV? It's the weight of the edge between U and V. So this is U and this is the V. This is the edge between them, and the weight of that is 4, correct?
Yes.
Okay, so this is 4. So what about V dot key? What is the key of V? V is here.
Is it infinity?
Yes, it's infinity. It's infinity. So this is also true. So what we do is that, so this is true and true. So we can execute the next 2 lines. And what we do is that we associate V with a key that is WV, which is 4. So we reduce its key from infinity to 4. And then we we also change its parent to U. So U is A. So we say its parent becomes A. Correct? Okay, this is the change that we make for the node V, correct?
Yeah.
Yep.
Okay, so we finished the iteration at B. Next, we're going to start iteration at H over here. So, so let's say, is H a part of the Q?
Yes.
Okay, so let's say what is WUV and what is V dot key? So what is WUV?
The 8.
Yes, WV is 8 and V dot key is
Infinity.
infinity. So here you can see that in every iteration of the for loop, what we do is that we compare the weight on the edge between the node U and its neighbor, one of its neighbor, and against the neighbor's key. So if the weight is less than the key, then we are going to reduce the key to this weight. And also we're going to change the parent of the node U, sorry, the node V to U, correct?
Yeah. Sure.
Okay, so this is what we do. So here we have WV as 8 and V dot key as infinity. So we can reduce it. So now we are going to reduce it to 8. And then we are going to set its parent to U, which is A. Okay, so then we finish the iteration at H. So then we finish one iteration of the while loop, correct?
Yes.
Yeah, okay, so then here before we proceed, I need to update the weight that the keys that we just updated. So we updated the key for B and H. So I'm going to update it in the Q. So it becomes 4 and 8. Okay, so any questions so far?
No.
No? Okay, so then I'm going to proceed. So here we just finished this and we're going back to the while loop. And while the queue is not empty, so for sure this queue is not empty. So we're going to call the extract min function of the queue. So which elements are we going to extract? From the queue.
Would it be C?
No, C has an infinity key, right? So the extract min function always removes the element with the smallest key. So
Yes,
it is going to be B, right? So we remove B, so we have U as B. Okay. So every time when a node is removed, I mark it with the purple color. So this node is gone from the queue. So I mark it with the purple color. Okay. So, and let's say, what are the neighbors of B?
C and H.
Yes.
A, C, H. Okay. So then, let's say, okay, so we will start with A. So let's say V is A. Is A a part of the queue?
No, it's removed.
No, so it has been removed. So we don't do anything for A because it fails the first condition in the if statement. So we are not going to do anything for it. So we are only going to do something for C and H. So let's check its neighbor C over here. So what is the weight between U and V? What is the weight between of the edge between them? It's 8, and the key of this node is infinity. Can we reduce it?
Yeah.
Yes. So if we can reduce it, what we do is that as what we did previously, we reduce its key to the weight of the edge. We reduce it from infinity to 8, and then we're going to set u, which is b, as its parent. So its parent becomes b. Correct?
Okay, correct.
Okay, so then we are going to apply the same function over the other neighbor of u, which is h over here. So what is the weight between u and v?
11.
11. So what is the key of v?
Eight.
Yes. So can we reduce it by using this edge or this weight? I mean,
No.
write it
No.
over here. So WUV is 11 and the key is 8. So this condition fails, which means that we cannot reduce the key by using this edge. So we're not going to do anything for, then this is going to be a false. So we're not going to execute the next 2 lines, and we're not going to do anything for this node, for this neighbor, correct?
Yep.
Okay, so yes, so for now we finish the iteration for both C and H, and then here we need to update the key for C to 8, because now it has a new key that is 8. Okay, so then we go back to the while loop. While the queue is not empty, right? It's not empty. And so when we call the extract mean function over the queue, which node are we going to extract? Which node are we going to remove?
Either C or H. I don't know which one comes
Yeah,
first.
either
C.
C or H should be fine, because this is like in the emergency room, we got 2 patients with the same priority, same and highest priority. We just let any of them so go to see the doctor, right? So here, let's say, for example, we just follow the alphabetic order and we pick C. So C got to C, so C is removed. So I'm marking the node C with the purple color. Okay, so U is C, so I'm marking U over here. Okay, this is the node U. So here, so let's say it has neighbors, it has a lot of neighbors, B, D, and F and I, correct?
Yep.
So, but B has been removed because it removed from the queue because it has a purple color. So we don't need to do anything for this node, correct? Because it will fail this condition. Am I correct?
Yes.
Okay, so then we only need to do things for D, F, and I. So let's start from D. So the current key of D is infinity, and the weight between of this edge between C and D is 7. So can we reduce the key of D?
Yes.
Yes. So what we do is that I'm not going to repeat the code over here because we just repeated it for 2 iterations. So I'm just going to apply what we did before over here. So we are going to reduce its key to the weight of the edge and change its parent to U, which is C. Okay, so then we move to the another neighbor of C, which is F. So currently F has a key that is infinity. So we can reduce it to the edge's weight, which is 4, correct?
Yep.
Okay, so we are going to reduce it to 4 and its parent becomes C. And then we're going to check I. So, okay, so currently I has an infinity key, so we can reduce it to the edge weight, which is 2. Okay, so then this is what we do in the iteration in this iteration of the while loop. So we we just changed we just extracted the node C and update the key for 3 of its neighbors. And then we're also going to reflect the change of the weight in the queue. So it becomes 7 and F becomes 4 and then I becomes 2. Okay, so then we go back to the while loop. The queue is still not empty. We're going to call the extract min function. So which node are we going to extract?
I.
I, yes, because I has the smallest key, that is 2. So we're going to remove I. So okay, so I'm going to mark I as purple, and so this is I, okay, and so let's say I has 3 neighbors, but only H and G are still in the queue. C is removed of the queue because it has a purple color. So then let's go to check either H or G. So let's say for example we start from H. Can we reduce the key for H?
No.
So currently it has a key that is 8. The edge weight between this node and H is 7. Can we reduce it?
Yes.
Yes, we can reduce it. Yes, we can reduce it by 1, so it becomes 7, and then we update its parent to I. Okay, so then let's do this for G. Okay, let's do this for the other neighbor. So G. So currently G has a key that is in infinity, and can we reduce it?
Yeah.
Yes.
Yeah.
So we can reduce it to 6. Okay. So then this is what we do for in the iteration of I. And here I'm just going to update the key for H and G. So it becomes 6 and 7. So then we go back to the while loop. The queue is not empty. So we're going to call the extract min function. Which node are we going to extract? F. So F is removed. I'm going to give F a purple color, and then F is removed. Let's check F. Okay, so F has 4 neighbors, but only D, E, G are still in the priority queue. So then let's do it. Check it for D first. It's neighbor D first. Can we reduce the key of D?
No.
No.
No. So 7 is more than 14, so we cannot do anything for that. But can we reduce the key for E?
Yes.
Yes, we can reduce it to 10, correct?
Yes.
And then we update its parent to F. Okay, and then let's check G. Can we reduce the key for G?
Yes.
Yes, we can reduce it from 6 to 2. Okay, so let's see the changes. So we reduce it for E and G. So E and G becomes 2 and E becomes 10. Okay, so then we are going to call the extract min function again. So which node are we going to extract?
G.
G. Yes, G has the smallest key. So I'm going to mark G as purple. And then this is G. Okay, so G has 3 neighbors, but only H is still in the priority queue. So can we reduce the key for H by using G?
Yeah.
Yes, we can reduce it to 1. And change its parent to G. Okay, so then here we just So next we need to call the extract mean function, and then we remove h, correct? Correct?
Yeah.
Okay, so yes, we remove h, and then h is gone. But here we can see that all the neighbors of h have already been removed from the priority queue, so we are not going to do anything for its neighbors. And then so we just call the remove function again. So then the extract mean function again. So which node are we going to extract?
D.
D. Okay, so we remove D, and we're going to mark D with the purple color. So here, E is the only neighbor of D that is still in the priority queue. Can we reduce the key for E?
Yeah.
Yes, so we can reduce it from 10 to 9, correct? So we are going to change to reduce it from 10 to 9, and then its parent becomes D. So we update it. And then finally, so the queue only has one element, so which is E, we remove it. And then we mark it with the purple color, and then we're not going to do anything because all of E's neighbors have been removed from the priority queue. And then we end up with an empty queue, so the whole algorithm terminates. Okay, so yes, this is the output of the algorithm. But so remember that our objective is to find a subset of the edges that can help us to connect all the nodes with the smallest total weight. But what are the edges that we need to pick? So in BFS, we recover the shortest route by using the parent, correct?
Yeah.
Yep.
Here we recover the edges that we pick by using the parent. So for this node B, its parent is A. So we are going to construct the road between A and B. And for this node, its parent is B. So we're going to construct the node between B and C. For this node, D its parent is C. So we're going to construct a road between C and D. For this node, for node E, its parent is D. So we're going to construct the road between D and E. F's parent is C, so we're going to construct a road between F and C. G's parent is F, so we're going to construct this road. H's parent is G, so we're going to construct this road. So I's parent is C, so we're going to construct this road. So the red color basically denotes all the edges that we need to or all the roads that we need to construct. So can we connect all the nodes by using the red edges?
Yep.
Yes. So let's say from A, you can go to B, C, D, E, F, G, H, I. So yes, it helps us to get all the nodes connected. Yes. So yes, this is the and if you want to calculate what is the total weight of the picked edges, it's also very easy. So we just need to sum up the weight, the keys associated with all the nodes. So for example, this node its key is 0. So it is going to be 0 plus 4 plus 8 plus 7 plus 9 plus 4 plus this 2 plus this 1 plus this 2. So this is the total weights of the edges that we pick in the minimum spanning tree. Okay, is that cool?
Yeah, makes sense.
So yes, this is the algorithm, and this is what the example that I used. And so, any question for me? If you have any question regarding the algorithm, just let me know.
What's the time complexity for this one?
Time complexity? Yeah, that's a very good question. And this complexity is really complicated. It is this O V log V plus E. Okay, so you don't have to remember it. For this algorithm, you don't have to remember the algorithm. Yes, I'm glad that you asked it. Yeah, cool. Okay, so any other question? No? Okay, so then after this class, you will have your homework 9, which is to implement the Primal's algorithm. And this is going to be the most difficult homework that you are going to have. So prepare 8 hours. So the main reason, the main difficulty comes from the fact that you are going to use a new data structure named priority queue. So when you are doing homework 8, so do you remember that in the PDF file, I said that you need to use queue, and in Java, linked list is the you can use linked list as the queue, correct?
Yeah.
And then I said, okay, if you want to use a linked list, so you need to check 2 resources. The first thing is like it's pretty much like the same as your real world experience. In real world, say if you're given a new car for you to repair, what you need to do is that first you read the manual of that car, and then you go to check some YouTube videos to see how do the other people fix those cars. So here for the linked list, I give you 3 links. So the first link is the API. It's the link to the API. API is essentially the manual. It's basically the manual of this data structure. And then I give you 2 links, which are the tutorials. I give you two links to the tutorials, correct?
Mm-hmm.
Okay. For this homework, you will definitely need to use the data structure named priority queue. It has already been provided by Java, but also you will need to check the API and also check a couple of tutorials. But I'm not going to give you the link. Instead, I want you to search for those links. Okay, and the reason is that when you go to your job, and you will need to learn to use some new data structures, and at that time, no one is going to give you the link. You are on your own. Okay, so that's why so starting from homework 8, I'm going to gradually reduce the level of help from my side and let you be more independent. So for this homework, you are going to search for these resources by yourself, read them thoroughly and have a good understanding of it, and then go to do your homework 9. Okay.
Okay, makes sense.
Okay, so and be prepared for the difficulties. It's really difficult, and the average grade, based on my past experience, the average grade on homework 9 is around 50 to 60. Whereas for the other homeworks, the average grade is definitely higher than 80. So be prepared. I expect you to struggle a lot with that, but you have to go through this process to be an independent programmer. Okay, so any question for me before you leave?
I know that on the syllabus, it says that we have a final project. When will we start our final project?
Okay, so the final project is actually a homework, but the homework is actually for you to implement an algorithm. But as I said, I'm starting from homework 8. I'm going to gradually reduce the level of help from you. So we've got homework 10 and the final project. The final project is basically a homework without any help from me. I'm just going to briefly discuss the algorithm to you in the lecture, and no skeleton code. But I'm not going to I'm not going to provide any skeleton code for you. So this will be in our last week. So let me say, this week you have homework 9, then next week you have homework 10, and in 2 weeks you will have your final project. Make sense?
Yeah, I'm sorry. Thank you.
No problem. Okay, so any other question for me? If no question, then that's it. Have a good weekend. Enjoy the weather.
Thank you.
Thank you.
Have a good one, Professor. Have a good one. Good weekend.
Oh, hey, Professor, how's it going?
Oh, good. How about you?
Good. So, I just figured I'd let you know I have a internship with Volvo, the car company, for cybersecurity.
Cool.
Yeah, I just thought I'd let you know because they asked some like questions and stuff. So, thanks to your help, basically. Yeah. Thank you.
Cool. Wonderful. Yeah. Congratulations.
Sure. Thank you. All right. Have a good day.
You too.